Hello, good morning everyone. My name is Izak Negron. Today I'm here with Saco, Adrian, Sinanan, and Perdomo. I'm here to present the SkillCourt autonomous problem. Now, when presented with this project by our client, we were initially given a problem, right? And the problem that was given to us was the technology and its involvement in sports, more importantly, the soccer ball launcher in itself. And the problem that it has is that there's not as much autonomy or diversity in the current market that's out there today. So SkillCourt is looking to find a solution to this problem that's out there. Now, when looking at the current market, we'll notice immediately that there's a large disparity between the prices of the products that are out there. And this is mostly due to the fact that the higher end products have more shop customization and they're much more convenient in terms of being mobile and in the sense of being battery powered. So, as a team collectively, we made certain objectives or goals for ourselves. So, most importantly, we wanted to make a soccer ball launcher that created a higher level of autonomy where one player can use this ball launcher by themselves. It would deliver the ball accurately and consistently to that player, and for overall to be more solo for that person and just bring new training methodologies to the player. Now, as for what motivates us, we understand that soccer is a sport that is revered across the globe, and we wanted to be able to bring something new, innovative, and something that would change the way that people train currently, and along with not only the soccer ball launcher, but the other SkillCourt products in unison. Lastly, the next thing about what our client gave us in terms of design specs, specifically what he wanted was to have a budget of about $2,000 to remain competitive with some of the brands that are out there today, to be effective within about 10 to 50 meters for the player distance-wise relative to the launcher, to have a battery life of about 3 to 5 hours, and in terms of movement of the launcher itself, for roll and pitch it was supposed to be about 45 degrees of movement, and yaw about 120 degrees.
So these are the initial alternative designs we looked into for the 3 degree of freedom platform. Now the following alternatives and the current one are 2 degree of freedom platforms at the top, since we decided we will control the 3rd degree of freedom with a lower motor that will provide the yaw rotation. Now we have 2 serial platforms, one with 2 platforms on top of each other with linear actuators, and we also have a gimbal system with arc links. Now the reason we didn't go with these designs is the serial double platform puts a lot of stress on the actuators, and it's also a lot slower to configure an effective position. While for the serial gimbal platforms, we look at a very high cost for manufacturing. Therefore, we came up with the following design for the 2 degree of freedom platform with pitch and roll. It's based on similar platforms used for race car simulators. Now it has 2 actuating links composed of revolute joints and 2 spherical joints, and 1 fixed link with a universal joint. We use 2 DC gear motors for the high torques the platform will experience, and as far as our component selection materials, we selected aluminum 6061 for the top platform and some components that won't experience a lot of stress, while low carbon steels and 836 steel and 4041 for other components that require more strength. Lastly, our universal joint selected was a 45 degree working angle and high torque capacity steel joint. Now here we have the design for the yacht platform. We have a smaller 1 gear motor with a high torque and low speed capacity. We added 4 rigid caster wheels at the bottom of the system to help support the platform while reducing the friction with these supports. And also we added swivel wheels at the bottom to be able to transport the platform. These are not shown in the picture, so they can be seen here. Now, as far as the analysis we did prior to designing the system, the motors and the flywheels given from our sponsor had the following specs. Therefore, we made a kinematic planar projectile analysis of the ball trajectory for about 20 meters at different velocities. And with this, therefore, we selected a working range of 0 to 45 degrees for pitch and roll. Now, in addition to this, we used MATLAB to look into the inverse position kinematics of the top platform. Now, I used a planar convention, and that allows me to solve for the pitch and roll separately. I'll have to look into doing them both together. In addition to this, initially I did the following analysis to select the length for a constraining the revolute length. Now, with this, I was able to get 35 degrees as a max angle. However, due to the use of threaded rods and tie rod ends, we can increase this angle by just changing that length.
Critical components of our soccer ball launcher was ran through simulation analysis. For the motor mounts, we used a natural frequency test. The motor has the specs of 60 hertz, and the first mode, the frequency of the motor mount came to 607 hertz, so it concluded it wouldn't fail through resonance. The tab assembly is made out of aluminum with a steel rod, and with a rated 50 pounds on top of it, we got a factor of safety of 14.5, as well as the arm links, where we added 100 pounds, and we got a factor of safety of 2.8. For construction of our soccer ball launcher, we use a horizontal bandsaw to cut the aluminum and also the steel, as well as a drill press and smaller hand tools so we can create holes and notches. We had a company called Autotronics help us out with the welding. They use a MIG welding to weld the aluminum, as well as universal joint support, and TIG welding to do low carbon steel, such as the universal joint itself. And some problems we had was the weld cracks, but as time progressed, we got a better machine. We got better welds on the aluminum platform. To do player tracking, OpenCV was used to track the player in a Visual Studio IDE. It was written in C++, and multiple programs were debugged to configure this. Out of the 6 options of tracking that we looked at, we had 2 that we compared here: selected region tracking and color tracking. The selected region tracking was slower speeds to track, as well as inconvenient setup time, since I had to click on the object that I want to track, and also it gave tracking errors since it's doing segmentation tracking. So if another object came into the picture, it will now track that other object instead of the one that I selected. However, color tracking was which was accurate, faster, and also had a pre-calibrated step. So once I get to choose what color I want, I set it up in my pre-loading, and I won't have to play with it again. It also was faster and went further distances, about 40 yards. As you can see in this GIF, as the camera takes in the image of the color, it's then converted into a binary, and we then thresholded a color. In this example, we use yellow. And the 2 vertical lines represents the area that we want a good shot, meaning it's lined up to that target. When it's outside of that area, to the right, you can see the see out program at the bottom, that it's telling the motor to move right or to move left. And if it's in the center, it's telling you it's good, it's safe to launch. And the bottom left right here with these taskbars is what I meant, that we could set it up how we want it in the beginning, so we don't have to do it again to track the color.
To ensure the motors are autonomously controlled, we have a couple notable components that we use. The flywheels and N-channel power MOSFET will be used to control speed using pulse width modulation or Arduino. And I use a shocking diode for the motor protection because we don't want any surge back. The shocking diodes are very efficient for saving power and protecting the motors. Next, for the 2 degree freedom platform, a monster motor shield driver, basically an H-bridge, is used to control the 2 degree freedom motors. Also using a Shockley rectifier, this will be able to give us speed, braking, and reverse motion so we can control the types of shots that a person wants. And finally, for the yacht movement, L2933 motor driver will be used for the same purposes as speed, braking, and reverse for the yacht movement. And Shockley rectifiers will be used for protection as a MOSFET, and here's a schematic of that circuit. At cost analysis, we initially had a theoretical cost around $2,500. This is using high capacity batteries, the utmost materials, and machining and labor. Luckily for us, we had free labor from Autotronics and our own personal time, and we had a cost around $1,500. $1,500 due to the low capacity batteries. These are lead acid. They were just used for the test capabilities of the flywheels, but for future purposes, we would use other high capacity batteries. And for commercial use, if lithium ion batteries were used, we might range around $2,000 between for manufacturing costs and lower components. For testing, we want to do multiple testing, including shot accuracy of the platform, types of shots, response time, and battery life and recharging. So what we did accuracy of the shot. This is just based on a person loading the ball manually. Here's that analysis. Now this looks pretty confusing, but so what we did is that when a player gets a ball, they become the center of origin. So all those blue hits, that's where the ball landed in comparison to the player. So we found for a degree to the left curve, which is one flywheel being faster than the other, we found a 22% error with most of the shots coming in the radius of the circle, which is about 5 feet. The same was done for the right, which we found a much higher percent of error. This might be due to the loading for a person being right-handed, perhaps. And finally, a center shot with both flywheels going the same distance, we found only an average percent error of 5% and a distance of 3 feet. Some standards we use include ASTM, ISO, NEMA, and ANSI. These were used for material, service robots, industrial robots, electrical, motor components, and rechargeable batteries. And for global design, soccer is a worldwide sport, so we understand that many cultures play the game. So we have a user manual in English, Spanish, German, and Chinese, as well as we use components that are recyclable, so as well as batteries that are not harmful to the environment and can be used for later purposes. And in conclusion, in future work, the launcher is capable of being autonomously controlled. It can provide multiple types of shots. It does provide accurate shots. And for improvements, we will use the SkillCourt app to integrate the autonomous nature, but to improve electrical and computer software programming of the system, as well as weight reduction and transportation and assembly time. If one were to assemble this, it would take quite a bit of time, so it would make it a lot simpler and make it a lot lighter, so it would be easier to transport from the field to a person's home, wherever they choose. And here's a division of responsibility. So each member had a crucial role in designing the launcher. Thank you very much.
Can you go back to your test result slide? Okay, great. Talk to me about why you think there were some errors, for example, in the 36 right.
Right. Okay. So I believe this error. This is what we did was like just putting the ball in with your hand. So this kind of simulates what other launchers that we mentioned before. A person's going to be doing this every time. So it's going to be a random variable when you put the ball through the launcher. But we want to do an automatic loading, which is for future work, where it will be a constant push through. So that will reduce the error, and we have 84% error for the right. Probably because if all of us are right-handed, we're going to do it one way mostly. So if for the left it was easier, the right it was harder.
As well as that every time the ball launches the motor, it reduces its RPM. So you can see that in the shot that it gets shorter and shorter. What he was saying with the linear actuator, the time it gets to reload back the ball, the RPMs will catch up to factor speed to do that constant shot.
Why is the middle one 12 feet and the left and the right 55 feet?
The problem we had for electrical, so the left and right, we use one launcher running at about full power, 60 volts, and the middle one using like 12 volts on each side. So that's why these only went up to about 12 feet, while the other two went to 50 feet. They were higher speeds.
So what would you say about your error in that situation?
It makes sense because when you have a larger pass, you're going to expect more error. You're not going to have a perfect pass right on the person's feet. So if you have a closer shot, it should be more accurate.
Yes, it's a lot easier to hit a target 12 feet away.
Exactly.
55 feet away. Right. So in these situations, if you can't make them all equal, you should highlight that part.
Right.
So I think this is interesting because again, the whole point of this whole thing is to try to predict and
reduce all the
right.
variables that we have.
So just keep in mind that when you're comparing things, compare equally.
Okay.
That's why also for that middle one, it's hard to see, but we made it for 30 inches for that radius because we knew it was closer. So there's less tolerance that we have for in terms of the air that we're going to be getting.
So then what? Okay.
So if I pass the ball to somebody 10 feet away,
Sure.
it should be more accurate than someone farther away.
So then how do you determine error in these ones?
If
It's just, you're doing counts,
Yeah.
right?
If it falls inside, then it counts as
Okay,
a
okay,
good shot,
gotcha.
but outside of that, then
Gotcha,
it's
okay, okay.
And why is the left side and the right side, one's elliptical area and one's round?
that was
It's just the wheels.
It's the scaling of the graph. This one had a
It's
bunch
a
of
little
figures.
Let's get on the graph, okay.
Yeah, it's a scalar.
Okay, motors, are they synchronous?
Synchronized, they can be controlled individually.
But they're not designed to be synchronous?
No.
So you can't control the speed of one versus the other?
Yeah, we
Yes,
can.
yes.
Yeah, we can.
We can synchronize it too, yeah, just adjusting the speed.
Okay, another question I had is, why is this not symmetrical in design?
Yes, one of the reasons why I didn't go with a symmetrical design, it was because it will occupy too much space.
But I mean, I moved that middle arm to the middle of my system.
The
Yes.
fixed arm to the middle of the system.
Yeah.
I didn't consider that option. In addition to this, since
Wouldn't that simplify your life? 'Cause-
Yes. But another reason for this is that we're planning on adding the reloading mechanism, which is added since this is the front of the launcher to the back, and it's you can imagine it as a cantilever extending from here, and I don't remember the length of it, but it's about 2 feet. Yeah. So we had that we considered that taken into account that we will use materials such as metals, but right now our current prototype is for our, since we have such a short time, we're going for lighter materials.
Okay, and then you used two DC gear motors that ran at 160 RPM.
Yes.
Are you going to ever run those at 160 RPM?
No. We're looking for a high torque capacity for the top platform, and through our research, and these were something the ones that we found that had a good torque capacity, and we're controlling them at a lower speed setting. We can show them the video where we test one motor controlling with the one before. Because at full power, they 600
Yeah,
160
I would
RPM
assume
is
so.
It goes crazy.
yes. Now what we're doing in this testing is we're controlling the angle where the shot will be through an Arduino program, and we have an encoder on one of the motors. We still need to add a second one to the second motor to control them both.
Okay, thank you.
If you can go back to your accuracy charts. So, you're measuring two types of error here, right? You're measuring a pass-fail, which is what you pointed out, or what you're measuring, but you're showing, you're telling me there's 22% average error based on pass-fail criteria, but you're also showing here a pinpoint at your accuracy, which you're not giving me that error, right? I don't know what my consistency is. All I know is that my ball is going to be somewhere in the vicinity of the player 20 or 78% of the time. So if you're going to show this, you might want to also show your statistically charts on what your accuracy is. Following that, you showed us the reader, or your color reader, but I don't know, besides if I'm standing right in front of it, how accurate it is. Did you test, what is it, 56 feet out, 54 feet out, if your visual reader can actually detect you?
It could detect. So it goes up to, we tested up to 40 yards. So the yellow, the binary white part, it gets smaller, but it has a moment function through OpenCV that it still detects that position with the point. So it goes up to 40 yards with our test. We didn't go past that.
So if you go to 40 yards, then test your accuracy up to 40 yards. Again, back to what I was saying. The safety aspect of it, your machine has a lot of sharp corners,
A moving
a lot
pinch
of
point.
sort of, yes, as well as someone running into it. If you are in a soccer field, if you run into it, you can potentially get injured. Furthermore, what I'm seeing a lot of your error is coming from your flywheels. If you look at your y-axis there, it's telling me that there's a lot of variability in the velocity that ball is coming out of, as well as your x-axis. You're showing me that when you're firing it straight, constant speed on both, you're more accurate than when you fire one faster than the other. So you might want to consider future designs in using a piston or a different type of system where you can control better how much force you're putting into the ball.
One other quick one on here is, it may be that your 0 point is inaccurate. Because if you translate this down,
Right.
your error
I see what you yeah.
matches the other side.
What we actually did was the origin. I said was the person. We actually had one shot that we used as a set, and then built these off of that.
And power. You're powering with batteries. If you start doing a lot of right or skewed shots, you're going to have a motor that is going to be expending more power.
Yep.
Later on, when you're doing a straight shot, you're going to have a motor that might not be spinning at the proper speed because you depleted all the power going to that motor. So maybe AC powered could be an option to consider.
Yes. Well, the motors these ball launchers come from are AC powered. Our prototype wanted to translate it to be portable, to be in the middle of the field. So we looked into powering with batteries. So that's a good.
Just a couple to follow up too. Almost every soccer field I've been on has a bunch of dew on the field too. So I know this is not your final design or anything like that, but of course that should be considered, right? Having open electronics.
Right.
Yeah.
Right.
Yeah, no, yeah,
right.
We all know
Just
that, right? But
some
just of
support,
course, yeah. Another question I have for you is, if you go back to some of the SolidWorks simulations you did, so there's two ways to use simulation, right? One way is to check your design for safety factor, which is what you did. Did you do anything, so you have these readouts, right? For instance, your tab assembly aluminum steel there has a safety factor of 14.5. To me, it might be over, right? And you can save some weight by reducing that assembly weight or size.
Right.
Did you guys use this in any way to try to make design decisions, or did you just test your specific set?
We did have simulations with thicker brackets, and it led to this one. But we didn't want to, through our manufacturing process, because since we have to cut them, we didn't want to go too thin. But I see what your point is saying.
Yeah.
Why? So you don't have confidence in your simulations?
Yeah, it's going to be safe.
But 14.5, why not go lower?
All right, yeah, because I see what
Yes. Ideally, we were only going to use a single aluminum tab. But our safety factor was below 1. I think it was 0.8.
Okay.
When I added the second tab, it went higher.
To 14.5.
Yes.
Okay.
Now the length of the tab is dependent on the length of the U-joint we selected. Since the point where the spherical joint ideally has to be aligned with the center of the U-joint. Now the U-joint is 5 inches high, so 2.5 inches. That's the length we needed for our
So
tab.
these are store-bought, or you make these?
the tabs.
Yeah.
Yeah,
We made it.
Okay.
Yeah, we could.
So again, for the future, right?
Yes.
If you're trying to reduce, this thing needs to go out to a field, someone needs to carry it out there. If you trust your simulation,
Something.
reduce the weight. Yeah.